来，那我们继续哦。你去上厕所，但是我继续。来，我看一下哦。这题啊，如果你要做的话，我建议你用什么？我刚刚有给你提示嘛，就是我的速度要等于1/2mv平方，对不对？可以吗？好，那问题是你的 v 等于 r omega，omega 跟 f 有什么关系？记得吗？v 等于2派 r 除以 t 等于2派 rf，所以这题的话，2派乘以0.2乘以10就等于4派，所以你的总能呢应该等于1/2乘以2.72乘以10^5公斤，再乘以4派的平方。哦，那我们算一下这个吧。0.5乘以2.72乘以10^5乘以4派的平方，所以应该等于2.15乘以10的几次啊？2.15乘以10的7次吧，Joule。2.15乘以10其实对。第二个，What's the black speed as it pass through the equilibrium point？所以代表说它要找什么最大的速度嘛？那我刚刚已经算完了呀，为什么呢？4拍嘛，那4拍大概多少？12.7 meter per second，approximately 12.6，差不多。来，再来是 angular simple harmonic oscillator，什么东西呢？我们现在知道一个东西，就是 F 等于 kx，对不对？那如果我今天乘上一个什么 radius，那是不是会变成 Rx？So it will be torque is negative k theta, but k it will be repeated symbol, so we use the kappa. So we call it the angular simple harmonic motion, which is mean it's the equilibrium position, and it will be oscillate a little of the angles between the positive theta maxima or negative theta maxima. We call it endpoints. 好，那通常这个 suspension wire 它是石英石，所以石英石它会有一个什么 restoring 的那种能力，就像橡皮筋你把它扭转之后，它会反转，对不对？那 kappa is constant, we call it torsion constant, torsion constant 叫扭转常数。Okay, it depends on the length, the diameter, and the material. 好，length, diameter, and the material. OK，那我们是不是也一样要找出它的什么 speed, period, and speed, period, and acceleration？那它的那个 torsion pendulum 的公式是这个东西，那 I 是什么？是 rotational inertia。好，rotational inertia 可以接受吗？好的，那我们先来看一下哦。Figure 15.10a shows a thin rod whose length L is 12.4 centimeter and whose mass is 135 grams, suspended at a midpoint from the long wire. Its period TA is measured to be 2.53 seconds. An irregularly shaped object, which we call object X, is then hung from the same wire, and the period TB is 4.76. What's the rotational inertia of the object about its suspension issues? 来看一下哦，图是这样子。哦，他说这个东西它的 period 是 2.53，但我现在挂了一个不知道啥东西的。好，他就讲 irregular shape whole we call the object is then hanging from the same wire. And its period TB is found to be 4.76. What's the rotational inertia? 那我们来看一下公式是什么哈？这个 kappa 基本上一样。Period is proportional to its rotational inertia square. So it will be 4.7 to 2.53 seconds. We didn't know. And the rub sustained at its midpoint. What's the rotational inertia? 它如果是这样转的话，我记得它的那个转动惯量多少 ？It will be 12 meter L square, right? Mass 12 mass. (0.135 kilogram) L square 0.124 square and have a square root. So please find the list first. So it will be 1.88 square multiplied by 12, 0.135 by 0.124 square. 那我们算一下这个。It's about 6.12 by the power of -4. 如果是 rotational inertia must be kilogram meter square. 6.12吧。Yes, that's right. And about the 15.4, the pendulum, the circular motion. 这题可以吗？来 pendulum circular motion。我们先来看几个重点观念哦。他就讲 ，a simple pendulum consists of a rod of the negligible mass， 就是我们假定是绳子嘛，就算是杆子，你也不准有质量。Let the pivot about its upper end with a particle attached to lower end. If a rod swings through only small angles, the angle must be less than 5 degrees. So it can be approximated a simple harmonic motion with the period. Okay? Period. In fact, I prefer this one. The pendulum L is mean the length of the wire, or you can say length of the string over the gravity. A physical pendulum has more complicated distribution of mass. That's why you need to consider its rotational inertia. So I is the pendulum's rotational inertia about the pivot. M is the pendulum's mass. H is the distance between the pivot and the pendulum's center of mass. Simple harmonic motion corresponding to the projection of the uniform circle motion. Yes, we call it the reference circle. So please read this. If you're okay, please tell me why it's a simple harmonic motion. 你想这个理由解释一下为什么 pendulum 是 simple harmonic motion. Let's see this one. If the angle is very small, so for the endpoint here, your gravity will be downward. You can just separate as one is parallel to your line and the other is perpendicular to your lines, right? And when you are just at the lowest point, don't forget, you have the speed, right? So T subtrate NG will be the NRV squared. Do you agree? So at the endpoint, your force just go back to your lowest point would be the NG sine theta, right? And it's approximate NG what? L theta. Do you know why? Because we know, please see the right triangle here. Since the angle is very small, okay, the straight line is similar to your arc-length. We call L is S arc-length. S for arc-length is L theta. Okay. So your force is approximately NGL theta. It's proportional to the theta. So we call it the K. So if the F is the KX, so your K would be what? NGL. So by the SHN, we know it will be N over K, the N over K. Hold on. What's happened? Oh, sorry. I lose one things. KX would be L theta, right? Because we just the displacement is always count from your equilibrium position. So the displacement is approximately the L theta is equal to arc length. So we can get a K would be the L NG over L approximately, since the angle is very, very small. So by the SHN formula, it would be 2 pi N over K, right? It would be 2 pi the N over the NG over L. So it's approximately 2 pi L over G. Are you okay? So once you consider restoring torque, the force acting on the bulb at force tension from the spring and the gravitational force, Fg. So if this is the pivot, okay? So the F of gravity will cause what? The gravity will cause the torque, but no torque for tension because the extending of the tension will pass through the pivot. So no torque for the tension, but there is a torque for the gravity, right? So we know the F, G. Okay, we will discuss here. So the torque caused by G, so we write torque of gravity would be the L, the NG, the sine theta, right? Would be the kappa theta. And it will cause the I alpha. Do we? And it will be NL square alpha. R alpha, R alpha. Yes, alpha. Is that okay? It's nothing, just the F is MA. And if you just combine with the, we call the lever or radius, okay? We get the A is R alpha. So the alpha would be R A over R. Okay? Just as this. Angle sine theta is I alpha. Alpha is for the angular acceleration at that point. Okay? And since we know just the straight line with the, we neglect the mass of the rod or straight line. So we just rewrite the pendulum's rotational inertia as the NL square. Okay? So and since the angle is very small, it will be angle NGLC the approximately I alpha. You can get the alpha would be the negative NGL I theta. And since we know the angular rotational SHN would be what? I kappa. Right? Nothing else, just like this. Right? I over a simple pendulum. Simple pendulum. Angular equivalent, the hallmark of the SHN. So the acceleration of the pendulum is proportional to the angular displacement, but opposite in sign. Which is mean if you just moving to the right, your force will be get you to the left. So its acceleration to the left increase until the bulb stops. Okay? So alpha would be negative NGLI theta. Kappa, we call it the kappa, right? Kappa theta. But what would be the omega is the omega should be K kappa over n. Kappa over n, so it will be the I NGL over I, right? Omega. Then the singularity is 2 pi over omega, right? So it will be a 2 pi the I over the NGL. I for the rotational inertia. Okay. And if you use the I as the NL square, it will be reduced to our pendulum is 2 pi L over G. Is that okay for you? Maybe you will ask why. That's something you should know. If the the theta is the cosine omega t, right? So the omega would be the omega sine omega t negative, and the alpha is the omega dt would be the negative omega square cosine omega t. So it will be proportional to your theta, and that we call omega. So since your alpha will be negative NGLI theta, we know it's the omega. It's okay for you? Think about it. For you, okay, please tell me. And by your omega is 2 pi over d. You can get the t. The period will be the 2 pi over omega. So you can get this one. I for rotational inertia. So you can know, we know the pendulum, the period is only proportional to the square root of its length, but not related to the mass of the object, which attached to the end. But the physical pendulum, maybe the mass is not distributed evenly, right? So for example, measure G. We can use the physical pendulum to measure the free fall acceleration G at a particular location on the Earth's surface. Countless thousands of such measurements have been made during the geophysical perspection. But how? For such a pendulum in 15.29, 15.29, let me see, what's the 15.29? This one. I didn't see anything, in fact. Maybe 29? Very strange. But that's okay. Just go back. Oh, it's mean formula 15.29, okay? And so we have the center edges series, which is mean we can find the icon, which means COM in the center of the mass. Okay. So if it is the rudder, if you rotate at the midpoint of the rudder, it will be 12 ml squared. And if I put an object just at the end of this, and that's the pivot, this will be at the end half L squared, so it will be 1/3 ml squared, right? So since we know the period is easy to measure. For example, there's one thing I should inform you that if you want to count the period, just swing back and forth by more than 10 times and just divide. Because maybe the time is too short to measure. So you just keep it swing back and forth by maybe 10 times, maybe 20 times, and you just take the record of the 10 times and divide it by 10. That would be more accurate. The tips of do the experiments. So it will be 2 pi the I and what? NGL, right? NGL, NGH, okay, NGH is equal NGL because I attach to the end. So it will be 2 pi the I is 1/3 ml squared over the NGL. Eliminate what? It will be 2 pi the L over the CG period. So by squared on both sides will be the CG over the 4 pi squared. Is no. Sorry, I want to get to the G, right? So I want to get a G here. So it will be 4 pi square L over the 3t squared is my G. A pi square, why? What happened? H is half L. H. Let me see what happened. For physical pendulum, the resulting force Fg sin theta of the gravity has the moment of the arc of distant edge about the pivot rather than the string length. Also, it's considered about the center of the mass, so your H now is half L. Okay. So PDF 452, please. 452.